off on Wednesday then, unless there are any other questions. And we were discussing area ruling, and remind ourselves about the basic concept here with area ruling is that we're going to essentially streamline the cross-sectional distribution of the aircraft as we're moving from the nose all the way to the aft section. So tip to tail in this case. So rather than having our nice circular fuselage here, we're going to contour this thing and essentially neck it down. So as we're increasing the cross-sectional area by adding a wing onto the fuselage, we're going to reduce that fuselage and basically give it this waist. And so there's a good example of this with this aircraft called minimum wave drag aircraft, and this was developed by Whitcomb again. We mentioned earlier he had worked on supercritical aircraft. So actually I have a nice model of this, so we can get a better idea of visualize this. This is not broken, as a matter of fact. Until I drop it. As far as I've never seen another model like this anywhere, so you were lucky to have this one. Yeah, that's when I drop it. Okay? Don't jinx me. And so this essentially follows that same approach. You'll notice what's happening here with the cross-sectional area of the fuselage. It gradually increases and it drops down where you have this wasted area, kind of this coat model, like midsection. As your wing is starting to increase the cross-sectional area, and then you increase it again as you get back towards the tail, where you're kind of losing that wing area. Because if you look at it, your maximum wing cross-sectional area is usually going to be right around here somewhere. Where you're starting to have the kind of the beefiest part of your wing, but then later on you start dropping it off when you get these later sections. Now, why don't we see this? Yeah, it's really what it boils down to. Hard to manufacture, because that's going to be really expensive to go through the process of doing it. No reason we can't do it. But if we could, even if it was cheap to manufacture, what's the other problem? Yeah, you end up, and you'd end up probably using the same number of seats here they do here. The airlines would just make it tighter, so it really suck. And sitting in front of the wing, like the window seat by the wing, that's where all aerodynamicists are supposed to sit, so you can see what's happening on the wing when you're flying. So from a logistical standpoint, just trying to get all your seating and your payload lined out there, that also becomes kind of really difficult to do. So all's not lost, because there are other ways that we can actually fix that problem. Actually, before we take this, we're going to talk about winglets on Monday. We talk about high lift devices. So they do have an example of a Whitcomb winglet on this as well. And so this was kind of really ahead of its time. We only have seen the advent of winglets on a large scale on airlines within the last decade. But the concept goes all the way back to the 60s and 70s, where again NASA demonstrated that these could have great potential savings in overall drag and then improvements in fuel economy by essentially adding these on. And then that was Whitcomb as well, who came up with that and demonstrated that concept. So, and that's essentially what's happening with a lot of aircraft now, where they say, oh, here's the aircraft as we purchased it, so we're just slapping winglets on the end like that. Now, all things being equal, right? If you look at a 787, you'll notice, oh, it doesn't have winglets on it. It's the newest aircraft to come out. Why doesn't it have winglets on it? Because they designed it to be the optimal airfoil and wing combination without having to put winglets on there. So winglets are essentially fixed after the fact. You've done your airfoil wing design correctly. First time around, you don't have to worry about it. It does give you an effective increased span when you go through that process. So, you are kind of boxed in into a particular span at an aircraft terminal. They won't let you increase your spanning because it's designed for 737. So adding winglets is an option to try to improve your overall performance. Thanks for bringing it over to us. Okay. Oh, before I forget, well, you guys are both here. For those who have been visiting Sarah in her office hours, she is due to have her baby next week, so she will likely not be in office hours. So please make sure you coordinate with Monica and Andrew if you have any other questions. and I'll let everyone know when Sarah comes back. Now, like we mentioned, this is really expensive to manufacture. Just having a straight tube is a lot easier to do. So there are other ways to get around that. Actually, let's look at our T38 first. Come back to this Tupolev 95 in just a second. I mean, this is kind of the best example. And you can see what they've done here with the fuselage. Notice, again, they have the inlet, so you end up having a little bit of a jump in your overall cross-sectional areas. You have the inlets here. They've done a really nice job through the process of wasping that waste down to minimize your impact of the overall compressible as you go through the process. Doesn't really save anything on the subsonic side, but it really makes a big difference when you're in that high subsonic and transonic regime. So that's kind of the best example. Now, one of the reasons that we don't see this on commercial airliners is we figured out another way to get around it. We see that on the Tupolev 95. So this has such a big effect, such a big impact on your overall compressible wave drag that you say, well, this is too expensive to manufacture. However, it gives us such a really good performance boost that it's worth adding other stuff on the aircraft and carrying that extra weight to get that overall drag coefficient reduced. And you can see the example of this with these things called shock pods on the trailing edge of the wing. So as you see the flow going from the left to the right, you'll notice this line right here. That's the formation of our shock wave. If you recall, back when we were looking at this from a 2D airfoil impact, and we have flow moving over the wing, it accelerates, and as it starts to decelerate on that unfavorable pressure gradient side, on the average pressure gradient side on the back, you end up having that back pressure form a shock. And so that shock wave results in a pretty high drag penalty. If you add these shock pods on the back, they actually provide this area ruling transition for you and give you an overall effective streamlined body. You know, think, wow, how could that, adding stuff on there really have the impact of the shock waves? Think again about it from the overall cross-sectional area. If you have something that looks more like this right here, you're more likely to have that adverse pressure gradient off the back, and you're going to be more prone to having those shock waves form. So if you can taper your entire cross-sectional area, even by adding other stuff on there, it gives you a big performance boost. So you see that in a number of different aircraft. You already saw the Tu-95 from the bottom side for the plan form view. You can see on our handling page, Victor over here, they called them Kuchman carrots, just kind of sticking out the back. But again, the Tu-95 is pretty interesting because when they found out about this, it was primarily them racing along in this counter-rotating propeller-driven aircraft at the same speeds as jet aircraft. And this thing would fly or cruise at about Mach 0.85, which is pretty impressive for a propeller-driven aircraft. Again, by adding these shock pods on the back. Now, we see these on all commercial airliners, or anything that's going to be this high subsonic regime. And what they do now is they essentially integrate these with the mechanical mechanisms that we have that control our flaps and our other control surfaces on board the wing. So these serve a dual purpose. They streamline those mechanical actuators and servos, but they also serve as shock pods to improve our overall cross-sectional. Now, there are other ways you could do this. This is kind of the traditional approach. And for those working on the airline concepts, you need to be thinking about, well, are we going to go something like this? Try to figure out how we're handling the interesting range payload point in our range payload diagram. Or you could try something a little more, innovative, such as a blended wing body. This is Airbus's latest concept, which you end up having a lot of aerodynamic improvements if you can run the numbers on this and show that this works. Boeing paired up with NASA a few years ago and did a lot of tests on what was known as the X-48, a large-scale model to demonstrate the concept before they decided what's been economically feasible. And you'll notice in this case for Airbus, what is it lacking? we have?
Windows.
Yeah, windows. So how do you deal with that from that standpoint? People like having windows, so they can see. You don't have to
Make it all out of glass.
One option is, well, just forget the windows. Windows are heavy anyway. You don't want to cut a hole in your pressure vessel, right? That's where you end up having concentrations at, and so you have to make up for that. Just get rid of them and replace them with virtual windows instead. So everyone's got, you know, their iPad attached to the wall, and you push a button, see outside or not. Most people don't look out the window, and it drives me nuts. Like you're on an airplane, just look out the window. Now I like this one. This is pretty different. So this is a University of Delft, Flying V. They say, well, you know, this doesn't work, you know, quite as well. Great for maybe just carrying cargo or payload. Even so, it's kind of hard to get stuff out in the wing. But what if we took that fuselage and then married it with that blended body design? Now you can still have your windows over here. But it's also really attractive from an area ruling standpoint. So if you plot this overall and look at how the area ruling behaves on both this body and this body, you know, you actually end up with really nice area rule profiles for your aircraft without having to go through the process of adding stuff like shock pods on where to be able to counter things. But can you actually get someone to fly on it is another question. So, you know, there's got to be, you know, a brave few that's willing to take that. Okay. Now, interestingly enough, you know, this is actually a problem with the F-35 because when it was originally being test flown, it ran through issues related to transonic acceleration. Recall that the whole goal going from subsonic to supersonic is just to get through transonic regime as fast as possible so that you don't have to worry about it. You don't want to spend any other time there, and it wasn't able to accelerate fast enough through that wall, which is essentially an area ruling problem. You'll notice because of the fact that it's got the big engine in the back there, then it's got its lift fan up here, which even if you're not, you know, using the marine VTOL version, this is, you know, ends up being filled up with fuel and other equipment in the back there. That ends up having not as good of an area rule profile as you would like it to have. For example, like you have on the F-22. And so you can see this kind of compared with other vehicles in terms of kind of the overall front view, you know, that profile view of the aircraft to get a sense of, you know, how it compares with other designs. What you will notice with something like Raphael, and it's kind of a nice, elegant, you know, contoured aircraft. But if you go back to our previous generation fighters with the F-18 and F-35, one thing you'll notice that the F-35 does a lot better than those do in terms of getting rid of all this stuff that tends to hang out here. Whether it is external mounts for your payloads and other hard mounts, or, you know, those servo pieces that essentially extend out from the aircraft in order to be able to keep your control surfaces on. You'll also notice, all things being equal in terms of cross-sectional area, the vertical tail can be a little bit smaller as well. Now, you only really have to worry about this if you're in the transonic regime. So if you don't have to kind of go overboard and, you know, try to push the envelope. That we always have to think about it from a logistical standpoint. All right. Now, final piece I want to talk about is this kind of overall drag prediction and what we're going to be doing for our drag prediction process. As I mentioned before, the lift piece is easy in the aircraft to build. And something like this, right, for our F-117. Actually, if you go back to it, you know, before we jump in and talk about drag prediction, you'll notice that the F-117, if you can kind of compare the profile or the side view or the planform view, they actually did a pretty good job area rolling it. So you'll notice that it gets pretty skinny back here, and that's the exact same time that it's actually getting wide. So that way it has a fairly flat area rule profile going all the way across. And, you know, even though it was not supersonic, it had really good high-speed performance. And even though it's kind of a you know, from a aerodynamicist point of view, it's not necessarily aesthetically pleasing, so really kind of a pretty aircraft. But going back to this, let's say, all right, you've been tasked with doing the drag prediction on something like the F-117, which has a lot of angular features and, you know, little mesh in front of the inlet here, so that way it keeps radar from going through and bouncing off all your engine components and then getting that signal back. It's got these flat panels here, all these kind of interference pieces. The wing is pretty easy, you know how to handle that, but how do you handle everything else and go through the process of actually predicting this? Because what you don't want to do is get it all sized, get it built, go out and fly it, and run into that F-102 problem. So you can't get up to or actually cruise Mach number for this. So there are three ways you can do this. One is wind tunnel testing. Tried and true method. Now, the problem that you run into is something we explored at the beginning of the semester, matching Reynolds number and Mach number. It's really difficult to do both of those. So you can do it in some very expensive NASA wind tunnels to be able to do that configuration, but even getting something like relatively small like the F-117 is really difficult to match. Also, it's very, very expensive. Requires a lot of power to actually go through that process. A lot of the larger wind tunnels that are run throughout the country are only run at night. So if you go to one of the Air Force labs, everyone leaves for the day, 5 p.m. comes along, that's when all the wind tunnels start powering up, because they can't power both the rest of the campus and everyone's air conditioner to the wind tunnels at the same time. The second approach is CFD. Great, because you do it all on the computer, even if it's a supercomputer. You can make a lot of changes pretty quickly and run through that process. I want to do that in the one tunnel test. Problem is, especially with drag, it's really hard to get correct. As I mentioned earlier, we still got at least another 50 years before computers get fast enough for us to do this process accurately. That leads us to the final one, and that's one that we're going to focus on and the one that we still use for the entire design process is the estimation. And really this boils down to taking something like this and figuring out what individual drag components are going to be and then adding them all up, just like we've already talked about for the homework for the Piper Cherokee. So this is the homework problem where we go through the process of looking at, well, what's my drag for an individual component, such as an antenna or my wheel pants or my landing strut. I'm going to figure out what the drag of that is by doing a wind tunnel test on that, or maybe some simple CFD on that, or going back and looking at the reference book. I'm going to use that cross-sectional area that drag coefficient is based upon, and then I'm going to normalize it by my wing area. And that allows me to find out what that normalized drag coefficient is going to be when added to my aircraft. And I can do that for any component that I'm going to add. Then it's just a matter of adding all those up. And that's what's done in this piece over here with our drag coefficients. So these are those non-normalized drag coefficients. Notice our pitot-static tube has a drag coefficient of 1. If our drag coefficient was going to be 1 for this entire aircraft, it would not fly. We would not be able to get it off the runway. But once we've normalized it with the size of that pitot tube, in relation to the size of the wing, the drag now is only 0.02. So it becomes much smaller and much more manageable. The second piece that we do is we come up with that equivalent flat plate area. And what that allows us to do is compare apples to apples now instead of apples to oranges. So that way we can take this aircraft and say, well, what's its equivalent flat plate drag ratio, and compare it with the same equivalent flat plate drag ratio for the Piper Cherokee. It gives us that same ruler or benchmark that we can do to come back to for that overall reference. I want to make sure that everyone is comfortable with both of these. They're really simple concepts, but you got to make sure we grasp them. Because this will be a fun easy. Any questions about either of these? All right, going back to this one, which I've already shown a lot. All we've done here, just to make sure everyone understands the breakdown. We have our part description. We have, some reference point that's gonna take us back to those details. Typically, it's gonna be dimensions. Then we have a reference area. Again, that reference area is gonna change depending upon how we define the drag coefficient for that particular part. A wing, it's always planform area. It's S. For something like a bluff body, like most of these down here, where you'll notice it says front, for all the bluff bodies, it's the cross-sectional area. Why? Because that's the important dimension. Okay? For a wing, it's looking at it like this. For our fuselage, it's looking at it like this for the cross-sectional area. But we're still going to take these values in and use them to go through that normalization process with that equation right there. All right? And that allows us to come up with all these numbers. We can add them up, and you notice the equivalent flat plate drag ratio calculation. Okay, just gives us what you down here in terms of the overall. Notice again, it's normalized by the overall wing area. So Piper Cherokee has an equivalent flat plate drag ratio of 3.9 square feet. And for a wing area of 160 square feet, that's pretty good. All things being equal, if you were to take this vehicle out and compare it to flat plate, your flat plate again is going to be about the size of that table. It includes the overall size of the aircraft. Now here's another example. Again, kind of a breakdown, and this is looking at the approach of, well, let's start off simple. If I want to make a wind tunnel model for this, or a CFD model, because it takes a lot of work to go through the CAD process. Make it a really high fidelity model of your aircraft in CAD software, then exporting that to CFD, then having CFD figure everything out and mesh it all. Because when it's running that solution, in a typical CFD solution, your aircraft is going to look like this, and then your entire domain that you're solving for is going to be about the size of the entire chalkboard. So it's calculating flow way out here, and flow way back here, and flow off to the sides and up and down, and that whole three-dimensional geometry. So you want to minimize all your complexities in your geometry as much as possible. So in this case, you're building it up and looking at the overall impact of adding each one of these components on. What's our overall drag? And this is looking at it in a slightly different perspective, where it says, well, what's our starting point that we have with our drag? And then when we start to do things in our aircraft, how does that change it? So this is basically our running drag value as we go through the process, and this is what our end-up drag becomes. And you can see how much we're adding each time we put an additional detail on to the aircraft. And each one of these by themselves is pretty small, right? But when you're adding all of them up together, you'll notice that becomes fairly substantial. And if you start to think about it from the standpoint of drag, 5% drag doesn't sound like a whole lot. 5% drag means that you're essentially using it's the same thrust specific fuel consumption on your engine, you have to use 5% more fuel. Which can add up, for an airliner to millions and millions of dollars a year. Okay? So you have to think about it from that standpoint when you go through this process. Any questions about that? All right. Finally, then, it takes us back to this list of steps that we had.